It's very likely that you're reading a lot about how much AI is winning across all sectors, but reading much less about how many projects, well, AI projects, are actually failing. And most AI project failures follow pretty much the same pattern. Typically, there is a leader that bought the narrative before they actually understood how the system works. The failure mode is not really technical, it's more epistemological, if you allow me the term. The organizations that are paying the highest prices right now are typically the ones that deployed first and, understood later. I'm Francesco, and this is Data Science at Home podcast. And of course, as you know, I've worked on AI deployments that worked, and of course, also on autopsies of the ones that didn't. The failure patterns are very consistent across sectors, scales, and also technical sophistication levels. At least that's from my personal experience and experience in my company, Amethyx. The common thread is not bad engineering, it is more the gap between what someone was told the system could do and what it actually did under so-called operational conditions, which are typically different than the demo conditions, as I will explain in a few minutes. Now, at Amethyx Technologies, when we evaluate whether an AI system should go into production, we run so-called adversarial testing before we run benchmark testing. The question is not how the system performs when conditions, of course, favor it. It's more about how it fails when, well, conditions don't. Most organizations never ask the second question. Now, let me go back to actually a use case that I hope many remember, which is IBM Watson oncology case. So IBM some years ago spent years and years and billions of dollars positioning Watson for oncology as a system that could recommend cancer treatments. We all remember that. I even made an episode some years ago. Check Google in that case. Hospitals across the US, across Europe, and also Asia deployed the Watson ecosystem. MD Anderson spent something like $62 million before abandoning the project entirely. Now, the system was generating treatment recommendations that oncologists described as pretty much unsafe and incorrect. The core problem was that Watson was trained on synthetic case notes and textbook examples, not on real patient records, as one would expect, from actual treatment outcomes. So the training distribution did not match the deployment distribution, which is typically the case in machine learning and data science. We have covered this a number of times. It's called statistical drift. Now, this is not, of course, an exotic failure mode. It's very much the most common failure mode in applied machine learning and data science. A model trained on one distribution of data will degrade when deployed on a different distribution, and real-world clinical data is almost never distributed like, textbook examples, right? And this, of course, goes across sectors. It's not just in healthcare. Now, the organizations that deployed Watson, in the case of Watson, did not ask about, training data provenance, which is something that is kind of normal asking now. They did not ask about distribution shift protocols. They asked about IBM's reputation and whether the demo was impressive. And, the demo was impressive. We have another use case, the Dutch benefit scandal. That's another big failure in automated systems, whatever machine learning has been involved. The Netherlands implemented an AI-driven fraud detection system for childcare benefit claims. The system flagged literally thousands of families as fraudulent. The families were subjected to pretty much aggressive collection actions. Many were financially destroyed, and some even lost their children to the welfare system. It was really a disaster. The system was wrong at pretty much industrial scale, the population scale, if you will. Now, the algorithm flagged even dual nationalities as a fraud risk indicator, which was both statistically incorrect and also, discriminatory if you think. The appeals process was designed around the assumption that the system was reliable, so it effectively rubber-stamped its decisions. What happened is that the Dutch government eventually resigned. The system had created a category of harm that was invisible until it had already processed tens of thousands of cases. The failure pattern here is different from Watson, if you think, but equally common. A model was trained to identify historical fraud cases, which were themselves artifacts of a biased enforcement pattern. The model learned to replicate the bias, and then the bias was automated. It was accelerated and pretty much made invisible behind a compliance process. What no one asked back in the days, on what cases was this model trained? What does fraud mean in the training labels? And of course, who labeled it? So these are the questions that we are still not seeing in the modern AI systems of today. There is yet a third case, the defense procurement miscalculation. The failure pattern is less publicly documented, but operationally significant. Several Western defense programs over the last decade have procured AI capabilities against vendor promises that did not survive contact with operational environments. The core error is assuming that performance on a vendor's task set predicts performance in the operational context. It rarely does. Operational environments are adversarials in ways that test environments are not. Operational data is also noisy, it can be incomplete, and often deliberately corrupted in ways that vendor benchmarks do not model. Now, a targeting support system that performs, for example, at 94% accuracy in a controlled trial may perform at, let's say, 71% under operational conditions with degraded sensor inputs, electronic countermeasures, and many edge cases that the training data never included in the first place. This 23-point gap is not an engineering detail. It's like the difference between a system that supports decision and one that corrupts them, right? Now, the organizations that avoid these failures are the ones that run so-called red teams against their own artificial intelligence systems before deployment occurs, not after procurement, of course. Now, what they all got wrong? Well, across these cases, and those and others that follow the same pattern, and I don't recall and I don't provide here in this episode, the failure is not primarily technical. It's more a failure of epistemics, as I mentioned at the beginning of this episode. The organizations believed the pitch. That's what happened. They evaluated AI systems the way they evaluate commercial software, by features, by reputation, by demo quality, and by vendor assurances. They did not evaluate them as statistical systems with known failure modes, distribution dependencies, performance envelopes that may not generalize, statistical drift being one of the major problems whenever data is involved, and so on and so forth. The vendors understood this and optimized for it. So the demos showed the system performing well on cases it was designed to perform well on. I call it cheating in a way, but yeah, they call it demo. The benchmark results cited conditions that matched the training distribution, which is, again, a form of cheating, right? The references were from deployments that had not yet failed or from deployments that had failed quietly, which is pretty much the same. Actually, it's even more dangerous. Now, a system that performs brilliantly in the conditions it was designed for and fails catastrophically in the conditions it wasn't, well, that's not a good system. It's a system with a well-concealed failure mode that the sales process was designed to conceal. So what smart organizations actually do? Well, the organizations that consistently get AI deployments right share one simple practice. They scope the failure mode before they scope the capability. And they ask, for example, under what conditions does this system fail? And what does failure look like? They build test environments that are adversarial. not favorable. They run pilots in the highest variance conditions, not the most controlled ones. They treat the vendor's benchmark documentation as a starting point for independent evaluation and not as a conclusion. They also build organizational structures that expect the system to be wrong some percentage of the time and root around that. Human oversight is not a compliance checkbox. It's a recognition that the model does not know what it does not know. And someone has to catch the cases that it misses. So what comes next? Well, the next wave of artificial intelligence project failures is already in the pipeline. Healthcare organizations that deployed large language models for clinical decision support without validating on their patient populations, but also financial firms that deployed fraud models without monitoring for distribution drift, and government agencies that deployed document processing automation without testing edge cases in the actual document corpus. And I can go on and on. The failure events are, in my opinion, just delayed, not avoided. They will surface as the operational deployment diverges farther from the conditions under which the systems were validated. The organizations that will pay the lowest price are the ones currently stress testing their deployment systems, not celebrating their deployment metrics. Well, I want to leave you with a take-home message. The pitch deck showed you the cases it got right. You needed to see the ones it actually got wrong. If you like this episode and this show, of course, don't forget to subscribe to our newsletter. You find all the links on the official website, datascienceathome.com.